Welcome to Ask and Learn.
In this problem, we have a spring-loaded piston cylinder device which is filled with air. The air is cooled until its volume decreases by 50%. We wish to calculate the changes in internal energy and enthalpy of the air. At specified conditions, air behaves as an ideal gas. And the gas constant of air is given by R is equal to 0.3704 psi absolute foot cubed per pound R. This is from our table. And the specific heats of air at room temperature, CV, at a constant volume is 0.171 BTU per pound mass R, and at constant pressure, the specific heat is 0.24 BTU per pound R. So again, these values are all from our tables. Now the mass of the air in the system we calculate as follows. M is the pressure in state 1 times the volume over the gas constant times the temperature T1. So we can substitute all these values in here. So that's a pressure of 250 psi into a volume of 1 cubic foot. This is all divided by the gas constant R, which is 0.3704, and that's psi cubic feet per pound R, multiplied by the temperature T1, which is 460 plus 460 R. So we get the mass of the air in the system to be 0.7336 pounds, or pound mass. Now from here we can find this final specific volume. The final specific volume, V2, is equal to the total volume of the system, V2, over the mass. And this is 0.5 times 1 cubic foot, so half the initial volume, over 0.7336 pounds. Hence we get the final specific volume of the air to be 0.6816 cubic feet per pound. Now, as the volume of air decreases, the length of the spring will increase. And the increase in the length of the spring, we'll call it delta X, is equal to the change in volume, delta V, over the area of the piston, AP. So this is equal to the change in volume, delta V, over the circular face of the piston, which is pi r squared, or pi d squared over 4. So that's a half pi r squared, or pi d squared over 4. Now this is equal to 4 into 0.5 cubic feet, so we bring the 4 above, over pi, and the diameter of the piston face is 10 inches, so that's 10 over 12 feet squared. And so we get the distance by which the spring will increase to be 0.9167 feet, which is 11 inches. So now that we have this distance, we can calculate the final pressure. The final pressure, P2, is equal to P1 minus delta P. So this is equal to P1, and delta P is delta F, the change in force, over the area of the piston, AP. And this is equal to P1 minus, we can write the force, the change in force as K delta X, where K is the spring constant of the spring, over the area of the spring, AP. So this is P1 minus K delta X over pi d squared over 4. And if we substitute our values in here, this is 250 pounds per square inch minus, we'll suppress the units here, 4 into 5 pound force per inch for the spring constant times delta X, which is 11 inches, all over pi into 10 inches squared. Hence we get the final pressure to be 249.3 pounds per square inch absolute. Now we can employ the ideal gas equation of state and find the final temperature. So the final temperature T2 is equal to P2 V2 over MR. And now we have all these values, so we can substitute them in. So P2 is 249.3. Again, we'll suppress the units, but that's psi absolute, times V2, which is 0.5 cubic feet, over the mass of the gas is 0.7336 pounds, and R is 0.3704 psi foot cubed per pound mass R. And hence we get the final temperature to be 458.7 R. Now that we have the final temperature, we can use the specific heats and calculate the internal energy change, delta U, and delta U is equal to CV delta T. So the volume constant specific heat times the change in temperature. So this is 0.171 BTU per pound R times the change in temperature of 458.7 minus 920 R. And we get the change in internal energy to be minus 78.9 BTU per pound. Now we can do the same and find the change in enthalpy. The change in enthalpy is the pressure constant, specific heat, times delta T. So this is 0.24 for CP BTU per pound R times delta T, which is again 458.7 minus 920 R, and hence we get the enthalpy change to be minus 110.7 BTU per pound.